Math Humans. We're going to do 3.2 today. We're going to be talking about the probabilities of and or. So our objectives are to calculate the probability of and then the probability of or, talk about mutually exclusive, and then we're going to talk about independent events, and then the at least once rule. So we've written down and. A couple of things before we get started. And means that both things have to happen at the same time. So if I want the probability of A and B, that means that both A and B have to happen at the same time. The probability of and is the most restrictive. The probability of or means that one or the other are either or. So then the probability of A or B means that either or A and B could happen. The next weird word that we have for vocabulary is mutually exclusive, ME. So mutually exclusive means that two events cannot happen at the same time. Mutually means the two, and exclusive means exclusive. Wow, that's just bad. So we'll just stop there. ME means that two events can't happen at the same time. So sometimes we would say that rain and sun are mutually exclusive unless you live in Arizona, because in Arizona those two things happen all the time. Okay, so those events would be not mutually exclusive if you lived in the state of Arizona. All right, for our first example, we're going to go back to a dice chart. Okay, so example number 1, and we are going to have two dice again that we are rolling. Okay, and so I'm going to bring back our dice table. So here we go. Okay, so remember that this is die number 1, and this is die number 2. And then the big numbers are the sums, and then I wrote the little numbers at the top because we're going to need those in this particular example. So this would be a 1 on the first die, a 1 on the second die. This number right here would be a 3 on the first die and a 3 on the second die. Okay, so let's say I wanted to define my events. So I'm going to say event E is that the sum is equal to 5. Well, and if I look at that, there are 1, 2, 3, 4, so that's going to be 4. Okay, the probability of F, and then actually I'm going to do these in pink. Okay, and then I'll change colors with each one because we're going to need to know that. So let's make F purple, and F is going to be that both numbers are even, and that means on the die both numbers are even. Okay, and so if we do that, it's going to be 2, 2, and then it's going to be 4, 2, and then 2, 4. None of those guys. 5, 1, 5, 2, none of those guys. 6, 2, 6, 4, 6, 6. And then I'm looking 4, 6, 3, 2, 6, and then none of those guys. So those should be 9 if I got them all. Okay? And then the last one that we're going to do is G, and that both numbers are less than 5. Okay? So the green ones, both numbers are less than 5, are going to be this, and notice that I'm going to have some overlap. Okay, so there's an overlap, there's an overlap, overlap, and then these guys, and then both numbers are less than 5. There's one, there's one, there's one. Ooh, my green pen is dying. Sad day. Okay, I think that's all of both numbers are less than 5. And if you count all of the green ones, there are going to be 16 of those. So then now let's look at, and hopefully the colors make sense, so we're going to see where we have things overlapping. So for A, I want to know, are E and F mutually exclusive, meaning they don't happen at the same time. So that's going to be pink and purple. So do our pink and purples overlap? Okay, so mutually exclusive means they don't happen at the same time. And if we go back and look at our chart, we'll notice that pink and purple never overlap. So this is a yes. So for B, I want to know, are E and G mutually exclusive? So do I have pink and green that overlap? You can't see that, sorry, my bad. Are pink and green going to overlap? And we see several, when you can't see both, so it's hard to show. So I have pink and green that are happening at the same time. So this is not mutually exclusive. And then for C, I want to know, are F and G. So F was purple and G was green. So are those two colors mutually exclusive? So I'm looking, do I have any purple and green overlap? And indeed I do. There's one, there's one, there's one. So these are also not mutually exclusive. And we'll add a yes, mutually exclusive. Okay? So remember that mutually exclusive means that events cannot happen at the same time. So then what I want to talk about, and I'm going to do it right here because I want to be able to illustrate this on the dice chart, is what if I wanted the probability of A or B? Well, this is going to be the probability of A added to the probability of B minus the probability of A and B. And I call this the probability of the overlap. So if we were calculating probabilities on our dice chart and we had places where those probabilities overlapped, then we would have to subtract those areas where they overlap. All right, so for example number 2, we're going to be playing with cards. Okay, and so we're going to draw a single card from a 52 card deck. Okay, and we're going to be looking for the probability of a club or a face card. So you always want to be really careful that you pay attention to what's in your probability. So then I'm going to do each of these separately. So the probability of a club, remember that there are 13 in each different suit. And then the probability of a face card, so remember that the face cards are king, queen, jack, and then there are times 4 suits, so there are 12, okay, because 3 times 4 is 12. So then this is going to be 12 out of 52. When I'm doing the probability of and or, I don't reduce until I'm done because it's going to make my math easier. So then the probability of a club or a face is going to equal the probability of a club plus the probability of a face, and then minus the probability of overlap. And I'm going to write that as club and face. So I neglected to do that one, so let's do that one. So the probability of a club and a face card is going to be 3 because there are 3 per suit, so there are 3 club face cards, okay? So then my probability of club or face is going to equal the 13 over 52 plus the 12 out of 52 minus the 3 out of 52. So this is 25 minus 3 is going to be 22 out of 52. And if you reduce the fraction, you're going to get the club or the face is equal to 11 out of 26. Okay? So you always want to think about what are the individual probabilities and what are the probabilities where they overlapping. Okay? For our next example, example number 3, we're going to toss a coin. So we're going to toss a coin, and then we're going to roll a dice. Okay? So I want to know the probability that I get a heads or that the number is 5. So let's think about our outcomes. Okay? Alrighty. So we're going to do this a total of 12 times. Actually, we're just going to roll. So I can get a heads and a 1. I could get a heads and a 2. I could get a heads and a 3, a heads and a 4, a heads and a 5, and a heads and a 6. I could also get a tails and a 1, a tails and a 2, a tails and a 3, a tails and a 4, a tails and a 5, and tails and a 6. Okay, so those are heads or tails are my 2 outcomes from the coin, and then when I roll 1 dice, I have the 6 possibilities. So my total number of outcomes is 12. Okay, so the probability of getting a heads is going to be 6 out of 12, and remember, I'm not going to reduce the fraction. The probability of getting a 5 is right here. There are 2 out of 12, and then the probability of a heads or a 5, sorry, I need to do the and. Let's make that, there's the and. The probability of heads and a 5 is just this guy right here, right? So he's going to be 1 out of 12. So then my probability of heads or, I'm going to circle it, a 5 is going to be the probability of heads plus the probability of getting a 5 minus the probability of heads and 5. Okay? So this is going to be, the probability of heads was 6 out of 12. The probability of a 5 was 2 out of 12. They overlapped. They met both criteria. So 6 plus 2 is 8, minus 1 is 7, so it's 7 out of 12. So the probability of getting a heads or a 5, remember or was add and subtract where they overlap, is going to be 7 out of 12. Okay? All right. In our next example, we're actually going to use a table of information. So this is example number 4. And so 250 people are going to recently purchase a car. Oops, not care, but a car, and they were questioned. And the results of those questions are going to be in the table. So we're going to have a new car, and they're going to have an old car. So maybe they bought a used car. I guess old is not very nice. Let's put used, and then total. And then that's going to be this part. Okay. And then up here, those customers were satisfied, not satisfied, bummer, and then here was the total. Okay, so if I fill in all the numbers, so I had 92, 83, 28, 47. So if I add the new car people, there were 120. The used car people were 130. We were told that 250 people were questioned. A total of 175 were satisfied and 75 were not satisfied. So now let's do some probabilities from our cool little table. So I want to know what's the probability that they bought a new car or they were not satisfied. Okay? So if we look at the probability of, because this is the probability of or, remember it's going to be the probability of new plus the probability of not satisfied minus the probability of new and not. Okay? Alrighty? So then my probability of new is there are 92 and not satisfied. Sorry, if we look all the way over here, there were 120 people that bought new cars. I was having a brain fart there for a moment. So 120 out of 250 is going to be, we're just going to leave it like that. We're not going to reduce. And then the probability of not satisfied, the not satisfied people were going to be 75 out of the 250 because this whole column is the not satisfied. And then the probability, I'm just going to write and, so new car and not satisfied was 28, okay, right here. So this is the new car line, this is the not satisfied, so it's 28 out of 250. So then my probability of new car or not satisfied is going to equal the 120 over 250 plus the 75, let me scoot my paper up so you can see, out of 250 minus the 28, that's an 8, out of 250, and we get that probability of new or not is going to be equal to 167 out of 250. Well, that's kind of sad. Okay, so sometimes we can do probabilities from a table instead of just doing it from like a dice chart or rolling coins or some such thing. The last thing that we have to talk about today is an independent event. Actually, I lied. We have a couple of things to talk about. The next to last thing is an independent event. An independent event is a little bit different than mutually exclusive. It says if the occurrence of one event has no effect on the probability of the occurrence of the other event. Okay, so if two events are independent, okay, if independent, the probability of A and B is going to be equal to the probability of A times the probability of B. Alrighty, so remember, we're not talking about mutually exclusive. We're talking about if one thing has no effect on the other. So let's do an example. Example number 5 says we're going to toss a coin 4 times. And I want the probability that all 4 tosses land heads, which is kind of an interesting probability, okay? So if you think about it, every time I toss a coin, it's an independent event because it has no effect on what's going to happen the next time I toss the coin. The probability of getting a heads, is 1 out of 2. So then the probability of getting all 4 tosses heads, my first toss is going to be a half. This is toss number 2. This is toss number 3. And this is toss number 4. Okay? So this is toss 1. This is our second toss. This is the probability on the third toss. And this is the probability on the fourth toss. So the probability of getting all 4 heads, each of the 4 tosses, is going to be 1 over 16. So then if I write the probability, let me get my computer back. If I write the probability of all 4 tosses heads, it's going to be 1 out of 16. Okay? All right. I have just a couple more things for us, and then we're done. Okay? So example number 6 is going to be pulling marbles out of a bag. So we're going to have a bag of marbles. We're going to have 4 white, and we're going to have 5 red. So we have a total of 9 marbles. Okay? So we're going to draw a marble, record the color, and then replace. This is often a really important thing, meaning that I put that marble back in the bag. And then a second marble is drawn. So if we think about what happens when I don't put that marble back in, it changes the probability on the second one because now there would be less marbles. So then the second marble is drawn, okay, and then we're going to do the same thing. We're going to record the color. So I want to know what's the probability that the first marble is red and, keyword, second marble is white. Okay, so this is an independent event because it doesn't, pulling marbles out of a bag doesn't affect what happens on the first or second draw. So my probability of red is going to be 5 out of 9. My probability of white is going to be 4 out of 9. So my probability of red and white is going to be 5 over 9 times 4 over 9, which is 20 over 81. So the probability of red and white is 20 over 81. So sometimes the probability of and is really interesting. Okay? The last thing that we have to talk about is the probability of at least once. Okay? So that means if I'm going to have n trials and they're independent events, okay, then the probability of A is going to be the probability of A happening one time, and then the probability of A bar is going to be the probability of A not happening. Oops, I think I got a few too many things in there. Okay, and then the probability of at least once is going to be 1 minus the probability of it not happening raised to the number of times that it happens. Okay, so we're going to do one last example, and then we are done for today. And I know this is a little bit long, so I appreciate your patience. Okay, so our last example, example 7. The probability of seeing a falcon near the lake during the day is 0.21. So the probability that a bird watcher will see a falcon at least once in 8 trips to the lake is what we're going to try to find. So we know that the probability of seeing a falcon near the lake during the day is 21%, or 0.21. I want to know what's the probability that I'm going to see a falcon at least once in 8 trips to the lake. So as we do the problem, I'm going to write the probability of seeing a falcon is 0.21. So then the probability of not seeing a falcon is going to be 1 minus 0.21, which is 0.79. So the probability of not is 0.79. So the probability of at least once in 8 days, remember the formula is 1 minus p raised to the n, so it's going to be 1 minus, here's our probability of not, remember a bar is the probability of not, so it's going to be minus 1.79, and we have 8 total days. So when you put this in your calculator, you need to be careful that the 8 goes with your 0.79, and you're going to get 0.848. So there's the probability of seeing a falcon at least once in 8 days is 84.8%. Okay, so there's an 84% chance that we're going to see a falcon in those 8 days. Alrighty, I think that is enough for one day. Thanks for being patient.